I'm going to talk to you today about work done over the past several years with Pat on semantics in the brain. And no, I didn't upload the wrong image. It is a map of Europe. It's meant to be there because I'm talking about the analysis of electroencephalographic data collected while participants were processing statements about the geography of Europe. The overall aim of the work is to see if we can detect evidence of semantic processing. So I'm going to jump right into the data, which should make Pat happy. But let me first just briefly say what made me very happy a few years ago was when I was having lunch with Pat, and he told me about his brain research. I was a student of Pat's in the 1980s, and he did some work on language and learning for robots. And when he offered me the chance to work with him on language in the brain, I didn't hesitate. There is no one who does science with such philosophical verve, and no philosopher who so enjoys performing theoretically grounded computations on somewhat messy data, getting the results, looking at them and trying to interpret them. It's an absolute joy to work on that with him. So, right on to the data. This is the experimental setup, and these experiments were conducted before I came on board. Briefly, a computer presented 48 spoken sentences to each participant, 10 randomized blocks of all 48 sentences, so the 480 trials. That's the data we got to work with. The sentences are all about the geography of Europe, very straightforward. The forms of the sentences on the bottom there, sentences such as the capital of Italy is Paris, which is false, and Spain is west of Russia, which is true. But what were the participants doing during this experiment? They were asked to determine the truth or falsity of each statement while the EEG recordings were made and their responses were collected. That was a set of city names, country names, and the sentences were simply about the capital, largest city, north, south, east, west. In approaching this work, the two fundamental claims established by Pat in his 2009 paper, which are important to get clear. And that's a paper on partial orders of similarity differences invariant between EEG recorded brain and perceptual representations of language. The two claims establish that when brainwave recordings are time-locked to the presentation of words in a sentential context, as they were in the experiment, as each word was presented to the participant, the time was noted. So when brainwave recordings are time-locked to the presentation of words in a sentential context, segments of those brainwaves, after appropriate transformations, can be identified as representations of those words. And these representations have approximate invariance across language speakers and across a variety of sentential contexts. As Pat points out, that was the case, it'd be very surprising how we communicate with each other. Secondly, significant structural similarities can be found between language constituents, and Pat was working a lot with phonemes, and the brain waves identified as their representations. What I show today is that structural similarities can be found between the brain data and the language data at the semantic level, and new methods to measure the strength of these structural similarities. And what this allows us to do is to assess the relatively better fit with the brain data of one semantic model over another. The three semantic models we're going to look at, and each one of them could be discussed for 20 minutes on its own. I trust a brief description will give you a sense of what they are. Many of you perhaps know WordNet, George Miller's work at Princeton with colleagues. It's a database of English organized around what we call sets of cognitive synonyms. And each word has several senses, and so you can choose the senses you're interested in, and you can so strongly restrict the context of the words that you're interested in. Latent semantic analysis is a statistical method to extract measures of word similarity from selected sets of documents, such as novels, newspapers, articles, psychology textbooks. So the context again is restricted, somewhat less so, not to what it's about, but to documents that are about certain things. And I say that because in contrast to the third model, which is a probability-based method that extracts word relations from the internet, with no restrictions on content, not even how that language is used. But you don't always get sentences on the internet. You get word farms produced. So, just to make sure it's clear, WordNet will have different senses, such as for Paris, the capital of France, the plant, the character and mythology, and lest we forget the town in northeastern Texas. Multiple word senses, the words are all connected to each other by links, usual, more specific, less specific, hypernymy, and is an instance of, has member. Those are the kinds of semantic relations that connected. We're really just look at the is more specialized or is less specialized, such as a vehicle and a car, a vehicle and a truck. I point that out because what we're going to be looking for is measures that show us how similar one word is to the other. And given the structure of word, there are various similarity measures that have been devised. I use 5 of them and take the average. One, for instance, measures the path length between 2 words. So 2 words like car and truck, up in, think of it as a hierarchy.